Thank you for introducing me. I'd like to thank the organizers, Ajay Jasra and Kengo Kamatani, for inviting me to this wonderful workshop. And today I'd like to talk about this particle rolling MCMC. And the title is a bit different from the one in the abstract, but we thought that the title in the abstract is too long, so we made it short. Okay? So basically, the talk is the same. And this is a joint work with my student, Naoki Awaya. And here's my outline of my talk. We first introduce motivation and model, which is a state space model, and also discuss motivation of rolling parameter and state estimation, and summarize this contribution of the paper. And then move on to particle rolling MCMC, starting with simple particle rolling MCMC and extend it to the one with block sampling. Okay? And moreover, we briefly go over theoretical justification of particle rolling MCMC, including a forward blocking and backward blocking. And finally, I give a couple of numerical examples. I noticed that the workshop is for high dimensional analysis, but in my case, at this point, at most bivariate observation vector. Sorry about that. So let me move on to the introduction. So we consider modeling economic time series during the long sample periods because I'm from the Department of Economics, so I'm interested in the analysis of a time series in economics. So we estimate model parameters, so we focus on time series, and we consider the risk management and policy simulation. But in the economic time series, it is well known that there have been major structural changes, such as the financial crisis in 2008. And also, some people say that parameters are not necessarily constant over the period and subject to the changes in the long sample period. Okay? So, to deal with the structural change in the economic time series, there are several approaches. One of them is to divide the sample period is several subsample periods. But in that case, we need to know how many structural changes in the sample period. And also, we need to know when the structural changes occur during that period. Okay? And the other approach is to fix the length of sample period, but implement the rolling estimation. Okay? But even though we have a couple of problems, like we need to decide the length of sample period, and also using the Bayesian approach, it takes a lot of time to estimate parameters and forecast, using MCMC. Some people say that the MCMC is not realistic because it takes too much time for complex model. And in this paper, we focus on the second part of the problem. Okay? We still don't know how to deal with the first problem, which is the length of the sample period. But let's say we find out the length of the sample period. Usually, we use like 5 years of data for a financial econometric model. But we focus on the second part of the problem, and we make the estimation time much shorter and improve the computational efficiency. Okay? So let me introduce the model which we deal with. It is just a state space model. Yt is an observation vector at time t, but in this talk, usually it is a univariate scalar or bivariate vector at most. Okay? And let alpha t denote the unobserved state vector at time t, and let theta denote the static parameter vector. Okay? And s colon t denotes y from ys up to yt, and the same is true for alphas. And p of yt given y1 up to t minus 1 and alpha up to t and theta is assumed to be p of y given alpha t and theta as usual. And also, p of alpha t given alpha t up to t minus 1 and theta is equal to assumed is assumed to be equal to P of alpha t given alpha t minus 1 and theta. Okay? But we also consider the correlation between yt and alpha t plus 1 because we are interested in applying our proposed method to the stochastic volatility model with leverage. Leverage means a correlation between yt and alpha t plus 1. So yt is stock returns, and alpha t plus 1 is log volatility at time t plus 1. Okay. Okay. So we sometimes use G for the likelihood and A for this state update, and mu for the initial distribution of the state. Okay. So we are interested in the posterior distribution of theta and alpha s up to t, given the observation y s up to t, with t is equal to s plus l. So the length of sample period is l plus 1, capital L plus 1. And pi of theta and alpha s up to t given ys given ys up to t is proportional to the prior density of theta and initial density of alpha and likelihood and the product of state density. Or, okay, here we have yj minus 1 for alpha j because of the correlation between alpha j and yj minus 1. Also, in the likelihood, yj minus 1, we also have alpha j minus 1 because we consider the correlation between alpha j and yj minus 1. Okay. So let me summarize the contribution of this paper first. So this paper considers the state space model for economic time series and proposes the efficient rolling estimation method for both parameters and states. Okay? And we also give the theoretical justification of the algorithm by proving the marginal density of the parameters and states. And our algorithm is based on the particle Gibbs. And also, our approach proposes, as a special case, the sequential Bayesian estimation method, which is an alternative to a very promising approach, SMC square, based on a particle MH. So our aim is not to provide the alternative to this SMC square, but for rolling estimation. But as a special case, our method can be used for the alternative method to SMC square. But the difference is that our algorithm is based on a particle Gibbs rather than particle MH. Okay. So let me start explaining particle rolling MCMC. So we start from a very simple approach, simple particle rolling MCMC, which we found very inefficient. And let's say theta alpha s minus 1, t minus 1 at time t minus 1 denotes a collection of particle for small n is equal to 1 up to capital N. And the corresponding weight, importance weight, is W, which is a discrete approximation of pi of theta alpha s minus 1 up to t minus 1, given y s minus 1 up to t minus 1. So we update these particles in 2 steps. Step 1, we add a new observation yt. Okay? So at time t minus 1, we only have information after t minus 1. Okay? Now we're going to add the new observations. Okay? So we update these particles to include alpha t. Okay? And also we update corresponding weights. And in step 2, we discard the older observation ys minus 1. So for alpha from s minus 1 up to t, we change the sample period by discarding the oldest observation ys minus 1. Okay? So let me use this figure to explain the step 1. In step 1, we generate alpha t given the current particles, and given y, including the new observation t. Okay? So originally, our sample period is from s-1 up to t-1, but we extend it to the time t. Okay? So by extending to the new sample period, we update the weight by taking account of the difference in the posterior density. And here, Q denotes the proposal density to generate alpha Tn. So we suppose that we may include the information of a new observation in this Q. Okay? And in step 2, we discard the old state and construct a new set of particles given by S up to T. So we also discard the information of y s-1. Okay? So we update the corresponding weights. So originally, the sample period is from s-1 up to t, but now we discard the information for s-1. We start from s up to t. Okay? So the corresponding weight is WST, and this is sort of discounting factor based on this old information. Okay? So here's some remarks. If some degeneracy criterion is fulfilled, which is usual in particle filtering, such as an effective sample size is less than half of the total number of particles, we resample all the particles by implementing MCMC algorithm. And also, we often use a prior density f theta of alpha t given alpha t-1 and y t-1 as proposal density q. Okay? That is very typical. But it is known to cause the weight degeneracy problem since the prior density does not take account of the new observation yt. But even if we are able to use a fully adaptive proposal density, as we shall see in an example of a linear Gaussian set space model, in that case, we can have this fully adapted proposal density. We still have weight degeneracy phenomenon, unfortunately. So let me show you this simple linear Gaussian state space model example. So yt is alpha t plus epsilon t. Alpha t plus 1 is assumed to follow AR1 process, stationary process. And for the prior of parameter mu and sigma square, we assume very less informative priors. So it doesn't, I suppose it doesn't really change the, our result. So window size is 1000. And in order to evaluate the weight degeneracy problem in steps 1a and 2a, we define two ratios. Okay? For the first ratio, R1T, we'll measure the change in ESS when we extend the sample period. Okay? And for R2T, we measure the change in ESS when we reduce the sample size, okay? Discarding the old observation. And here, ESS is just the usual definition of effective sample size. Okay? And take a look at these figures. So this is a trace plot of R1T and R2T. And this is a histogram of R1T and R2T. As you can see, for the first step, step 1A, it seems like things are doing okay, I mean, just fine. Sometimes going down below like a 0.1 or so, but usually around 0.9. Okay, so it's not really good, but it's not that bad. But for R2T, the problem is very serious. You know, most of the time the R2T is around 0.1 or so. So in step 2A, we have a serious weight degeneracy problem. Okay? So here in this example, we use a fully adapted proposal density, but even though we have very serious problems in step 2. Okay? So what we're going to do is to use a block sampling to fix this degeneracy problem. Okay? So we update these particles in 2 steps. In step 1, we of course add a new observation YT, and instead of generating 1 alpha, we generate a block of alpha from t minus k up to t. So in the simple algorithm, we just generate alpha t n. But now we generate a vector of alpha t minus k up to alpha t, given other parameters and set vectors, and ys minus 1 up to t, and construct a collection of particles with the importance weight ws minus 1 to t. And further, we implement the particle simulation smoother to improve the mixing properties. So we do the same thing for the step 2, but in a different direction, backward direction. So we remove the oldest observation ys minus 1 and generate alpha s minus 1 up to s plus k minus 1 backwards. Okay? So in a simple algorithm, we just generate s minus 1 and s, but now we generate a block of alphas and construct a collection of particles with the importance weights w and discard alpha, and of course ys minus 1 to update the information. Okay? So here's the figures of step 1. So what we do is to generate a block of alphas, alpha t minus k up to alpha t, rather than just alpha t. Okay? But in addition to this forward block sampling, we also conduct the particle simulation smoother, okay? Or going backwards. Okay? So we update this weight using the estimate of p. Okay? P of yt given ys minus 1 up to t minus 1, alpha t minus k minus 1. Okay? And for step 2, we generate a block of alphas starting from s plus capital K minus 1. We go backwards to generate. Okay? Basically, we are doing the same thing, but going in the opposite direction. And after we generate a block of alphas, we just discard alpha s minus 1, and starting from alpha s, we conduct the particle simulation smoother to improve the efficiency of the algorithm. And for weights, we update by using this discount factor. For basically, that includes the information of alpha ys minus 1, which we throw away in this step 2. So in forward block sampling, we move particles using the conditional SMC update for each n up to capital N based on particle Gibbs, okay? Which is discussed in the paper by Andrew of particle SMC. Okay? And we generate a number of candidates for each particles from M up to capital M, where the current lineage is fixed as one of the candidates. And the alpha t and m is also generated condition on alpha t minus k up to t minus 1. We determine which lineage is appropriate as a new lineage and compute its importance weight for each n. Here's the figure of what we are going to do in step 1. Let's say these states in a rectangle denotes the current lineage. So this is one of the lineage among the candidates. And from this lineage, we generate alpha Tn. And also from this particle, we generate those particles in a which is in a circle. Okay, so these are the particles that generate as a candidate, and after we generate the candidate, we pick up one of them. And let's say this lineage is selected. Okay, could be any lineage, but let's say we select this lineage, and after we select this lineage, then we conduct a simulation smoother to determine the final candidate. Okay. So the same is true for backward block sampling. And for backward block sampling, we generate the particle of alpha s plus k minus 1, alpha s plus k minus 2 in a opposite way, a backward way, and then stochastically determine the new values of alpha s up to t. Basically, we are doing the same thing in an opposite way. So we start from this current lineage and generate alpha s and alpha s minus 1. And we also generate other candidates. And let's say these four particles are the generated candidates. And for example, this lineage is selected. And after that, we discard this alpha s minus 1. And then starting from alpha s, we conduct the particle simulation smoother. Okay. And here's another problem, which is the initialization of the roaring MCMC. So in order to sample from the initial posterior distribution, it is straightforward to use MCMC methods as in the warm-up period for practical filtering. Paulson et al. In 2008. And, but SMC-based methods are preferred when we need to compute the marginal likelihood. Okay? That is another issue. And so we implement only forward block sampling to sample alpha 1 up to a capital A plus 1 to compute this marginal likelihood. Okay? And of course, if some degeneracy criterion is fulfilled, we resample all the particles by implementing MCMC algorithm. Okay? So we compute this marginal likelihood ys up to t in a recursive way. So once we have this marginal likelihood in the previous step, we can compute numerator and denominator using the weight and previous, okay, this conditional likelihood. Okay. And for the initial estimate, it is given by this recursive product. And for the first marginal likelihood, we just compute somehow generate the marginal the theta from posterior distribution and compute the sum of p hat of y1 given theta, which gives you p hat of y1. And for p hat of yj given y1 up to j minus 1 can be computed with the same way as in the previous slide. Okay? And let me briefly go over theoretical justification of PRMCMC. It's a little complicated, but let's say marginal density of parameters and state vectors of interest for the artificial target density. So this artificial target density is not the posterior density, but marginal density of this part is just the same as our target density. Okay, not the artificial target density. Our target density is this density, and this is the same as the marginal density of our artificial target density for the forward block sampling, where AJ is a parent index variable and KJ star is a random index. And for proposition 4.2, expected value of P of hat yt, P hat of yt given ys minus 1 up t minus 1 is actually equal to P of yt given ys minus 1 up to t minus 1. So this is an unbiased estimate of this guy. Okay? And also, proportion 4.3 is just the proof discussed in the widely at about 2010. So let me just skip that. Okay. For proportion 4.4, the marginal density for the parameter and state vector of interest for the artificial target density is the same as the density for the backward block sampling. Okay? So basically, the proof is the same as in the forward block sampling, but we can also show that our algorithm is not just approximation to the posterior density, but the exact approximation to the posterior density. Okay. And also, this inverse of p hat is an unbiased estimator of inverse of p of ys minus 1 given yst and theta. Okay. So I just skipped the details of the proofs, but if you are interested in, then please check our paper, which is in the internet or archives. So if you Google, then you can find out our papers, okay, just in case. So let me give you the numerical examples, okay? Okay, so let me start with the example 1, which I introduced in previous slides. And window size is again 1,000. Okay, the number of particles is said to be 1,000, and the size of block is k 1 or 2 or 3 or 5. So it is not that big. Let's say at most 5. Okay, for each n, we generate capital M particle path in the forward and backward block sampling. Okay. And here's a table for the number of resampling steps in a particle rolling MCMC with block sampling. And let me focus on these fully adapted proposals. So this is an idealistic case. For this case, the number block is at most 2 because even though we increase the number of blocks, the number of resampling steps does not change that much, and that is the same for a rolling estimation period and initial estimation period. So k is not that much. So for our case, capital M is taken to be 100 or 300 or 500, and for 100, 300, maybe the difference of 300 may be better, but in this specific example, M equal to 100 is enough because for k equal to 2, there's a significant reduction in the number of resampling steps. So we focus on subsequent examples. The case M equal 100 and k equal 2. And if we compare with the case of a simple sampling, the number of resampling is significantly reduced for initial estimation period and also rolling estimation period. Okay. And here's the histogram and scatter plots of R1T and R2T. Okay. And I mentioned that for R1T, the weight degeneracy problem is not that serious. But even though our method improves efficiency a lot in comparison with a simple sampler, and also for R2T, our method dramatically improves the efficiency in to overcome this weight degeneracy problems. So here in this example, we use capital K equal 2 and M equal to 100. And this is here a plot of R1t and R2t. As you can see, for our proposed method, both of R1t and R2t are close to 1. Okay? So there's not a big difference in ESS for our approach, but there is a big difference for a simple sampler approach. And here's the summary statistics of R1t and R2t. And for R1t, the mean is, for the simple case, simple sample approach, mean is 0.862, and our approach, block sampling approach is 0.975. So it is still much larger than the simple approach, but the main difference is in step 2. So in R2t, summary statistics mean of simple approach is 0.16, but for block sampling approach, the mean is 0.97. So the improvement is very dramatic by using our approach. And here's a plot of true posterior means and 95% credible intervals denoted by dotted black versus our estimates with a solid red for parameter mu and sigma square for loading estimation period. As you can see, there's a slight difference, but this estimation is very small if we compare with the other approach, which we shall see later on. And here's the estimate of log marginal likelihood. And true log marginal likelihood is denoted by dotted black here. And our estimates are denoted by red lines. Okay? As you can see, both of them are almost the same. And here's the difference between these estimate and true marginal likelihood. And these are very small. Okay? So it means our proposed approach is very successful. Okay? And as another example, we consider so-called realized stochastic volatility model. So I suppose you know stochastic volatility model very well, but you know these days we have additional information using the intraday data, intraday returns. We have additional information regarding the volatility. Okay? So that is called realized volatility or realized kernel, whatever. Let's say Y1t is daily stock returns, and Y2t is a log of realized volatility or realized kernel, any kind of realized measure. And Y1t is as before, not before. Y1t is exponential of alpha t over 2. So alpha t is a log volatility. And epsilon t is assumed to follow normal distribution. And Y2t is a measurement equation for log of realized volatility. And that is assumed to be alpha t plus some bias correction terms and noise. Okay? I don't really get into the description of the model that much, but this is one of the standard specification of so-called realized stochastic volatility model. So the volatility process, log volatility process, is assumed to follow AR1 process, and we assume the normal distribution, but we only consider the correlation between epsilon t and eta t. The correlation between epsilon t and eta t is introduced to express the leverage effect. So if there's a big decrease in this, today's returns, and then the volatility tomorrow becomes larger. That is called leverage effect. Okay. So using this model, we use data of a Standard & Poor's 500 index obtained from Oxford Mann Institute Reals Library, which is available for free. And initial estimation period is from January 1st, 2000 up to December 31st, 2007. So the length of sample size is 1988. And the rolling estimation started from the sampling from the posterior distribution using this initial sample period and moved the window until December 30, 2016. Okay? And in this specific example, the capital K, the size of the block, is assumed to be 10, and the number of particles in the block sampling, say 300, and the number of each particles in the particle MCMC is said to be 1,000. And for the comparison purpose, we implement a 10 MCMC iteration after each step of updates. Okay. And here's a trace plot R1T and R2T again. As you can see, almost both R1T and R2T are close to 1. So our sampling algorithm is very effective. And here's the summary statistics for R1T and R2T. And regardless of sample size, okay, the block size K, our mean of R1T and R2T are very close to 1. Okay? So regardless of block size for this R1T and R2T. But for the computation times, wall times using capital K equal to 5 and 10 and 15. So if you take a look at this, the case K equal 5, it takes a much longer computational time. But if you increase the K up to 10, then it is denoted by the red lines. The computational time becomes much smaller. But if you increase more block size, then the computational time becomes larger again. So that's why we use capital K is equal to 10. And here's the estimated posterior distribution function of theta, like a mu and phi and sigma square and xi and so on. And for the green line correspond to one update for MCMC, and blue line correspond to 5 MCMC updates, and red line correspond to 10 MCMC updates. And as you can see, so one MCMC update is not enough to get the exact estimate of posterior distribution of parameters. So that's why we use 10 updates in MCMC steps. And here's the trace plot of estimated posterior means and 95% credible intervals for parameters. And I just compared the 5 MCMC updates and 10 MCMC updates. As you can see, blue line is a little bit unstable. So if you use 10 MCMC updates, it seems like stable. So that's why we use 10 MCMC update. And here's estimated of a log margin likelihood. And red line correspond to the model with leverage, and black line correspond to the model without leverage. And as you can see, the model fits, the RSV model with leverage fits better than the model without leverage. And this is a well-known result in the stock market. Okay? So in a foreign exchange rate market or bond market, we don't find the leverage effect. But in stock market, especially index returns, we find significant leverage effects. Okay? And also, okay, this may not be a necessary part to my talk, but I got some comments. Why don't you compare with the previous method in the literature? So as a special case, our approach can be used as an alternative to SMC square. So we compared the method with SMC square in the framework of sequential estimation, okay, which is not our major purpose. But if we do that, let's say this part, okay, in the particle image update steps of SMC square, we use a random walk image algorithm using the theta star and c times sigma hat, where theta star is the current value of parameter theta, and c the tuning parameter, in our case 0.3 or 0.5, and sigma hat is the estimated covariance matrix based on the pilot run. Okay, so in case of tuning parameter c equal to 0.3, SMC square performs very well almost all the time, but sometimes it becomes very bad. Okay? It takes a lot of time for computing in SMC square. And if you take c equal 0.5, it becomes a little bit stable, more stable, but until the end of the estimation period, it becomes very unstable. Okay? But in our case, it looks very stable. Okay, this is the result of 10 rounds of SMC square and our proposed approach. So in comparison with SMC square approach, our method sometimes takes longer time, but basically gives the very stable result. Okay? And here's the estimated posterior cumulative distribution function of theta given y1 up to 1988 observation over 10 rounds of SMC square with the same tuning parameter c equal 0.3 and 0.5. And as you can see, the CDF based on 10 rounds of SMC square is very unstable. Okay? And here the gray line corresponds to the accurate estimate based on MCMC. But of course, it takes a lot of time to compute. Okay? And here's our approach. Okay? So except the case mu, almost all the times our approach gives the very stable estimate. But for the parameter mu, we may not have enough information regarding the parameter mu, so it is a little bit unstable. But if we compare with the result from SMC square, it is more stable. Okay? So the last figures may not be necessary for our talks, but based on some comments, we added this comparison part in the revised version of our paper. Okay? So this paper considers the state space model for the economic time series and proposes the efficient rolling estimation method for both parameter theta and states alpha s up to t, and give the theoretical justification of the algorithm by improving the marginal density of parameters and states. And our algorithm is based on the particle Gibbs rather than particle MH. So proposes as a special case the sequential Bayesian estimation method, which is which can be regarded to be the alternative to SMC square based on particle MH. But as I mentioned, that this is not our main interest to propose the algorithm. Our main interest is to propose the algorithm for efficient rolling estimation, which is very typical in economics time series data analysis. Okay, that's all. Thank you. Okay, let me.
Why is that? So what influences computational effort?
You mean this table?
No, the one when you showed in the second example.
Second example.
Decided that 10 is the right one because you had the computation.
Based on the, yeah. Because to generate this block of states, we use just information for state equation, okay, the sort of prior distribution for states. So as we make this k larger, then our proposal may not be very good to approximate the posteriors. So the rejection, I mean the rate becomes higher. So that makes the computation time longer eventually. Yes. So still we need to go through trials and errors to find a very effective K or capital M. But after several trials and errors, we can dramatically improve the efficiency in comparison with a simple algorithm. Yeah.
Any other questions or comments? That's good. That's time for second.
Yeah, thank you.